Hello. In our presentation, we are going to discuss the challenges that we can face while testing the nanoparticle using in vitro methods. Here I'm talking about nanoparticle from a focus or a point of view regarding their cytotoxicity. I am Nashwa Osman, and I am final year PhD student, and I'm expecting my viva next week, so finger crossed. There's different types of assay really to test the nanoparticle cytotoxicity or other assays that being used by other researchers to test the nanoparticle for different aims. But these assays, we can really start to summarize them in different categories. For example, some assays are applying the reagent after the cellular exposure to nanoparticles. So we're going to study one example of this is Nanoparticle assay. Nanoparticle assay is one of these viability or cytotoxicity assays, and that assay you are adding it to the end at the end of the experiment. And I have here two different methods for the same assay. For example, the first one is A and B. That assay have been done, and I've added the Nanoparticle reagent to the cells after I removed the nanoparticle plus 3 washes step by warm PPS. And the other one is C and D. These graphs, you are going to see the assay. The same assay have been done, but I've just removed the supernatant and left the monolayer without wash step. What we're expecting is still some nanoparticle on the surface of the monolayers. And what you can see here from the differences is slightly higher results or better results with the 3 wash step. You can see it is a narrower error bar, slightly higher than what you can see with applying no wash step. Usually, these two graphs are applied by different researchers that just either add the reagent to the reaction medium without removing even the nanoparticle, or literally just removing the nanoparticle. We might apply only a single wash step or no wash step at all and apply the reagent. So you can get higher error bars, plus you can get a false higher cytotoxicity compared to removing the nanoparticle. Because while you remove the nanoparticle, you apply 3 washes steps, you have literally cleaned the surface of the monolayer, you have literally efficiently stopped the further exposure of nanoparticle. When we followed the Nanoparticle for 3 hours, what we have seen is this low concentration of these nanoparticles here are of a higher viability compared to the low concentration. Plus, we started to see a recovery to 100 or even over 100. So the cellular recovery is happened. So literally, you are efficiently stopped the nanoparticle exposure after the 24 hours. But here, and that is saying the still nanoparticle on the surface of the monolayer, they are still exerting cytotoxicity effect, or there is an interference between the nanoparticle and the cell and the reagent, making the reagent uptake as less. What you can see here is higher cytotoxicity compared to this. They are not even compared. This could be applied by research, and we see many examples of them in literature where can be false claim of a higher cytotoxicity while it is not. Another type of assay, you can apply the reagent to the cells prior, applying the reagent to the cells prior to the cell exposure. So you add the reagent, then you add your nanoparticle. For example, we are going to have an example of this is the ROS assay by DCFDA reagent. We applied the reagent first for half an hour, then we washed the reagent, then we applied nanoparticle for 24 hours. Then after this, we removed the nanoparticle, done wash step, and we measured the NPS. What you can see is nice graphs of increasing the nanoparticle concentration is associated with increasing the ROS production. We'll see a different assay have been applied by a different method to measure the ROS. This assay is done by the degrade assay from Abacum. This is the Abacum code for it. This assay have been applied by removing the nanoparticle and applied 3 wash step. And here, after just removing the nanoparticle, we didn't apply any wash steps. As you can see here, with the wash step, you are seeing just literally a blank result with only the high concentrations are exerting a higher ROS compared to the negative control. But when we applied the same reagent but without efficient removal of a nanopart, you can see a decreasing trend. This decreasing trend really have been reported for many ROS assays that applied after similar exposures. They claim either there is a bit of quenching the fluorescent intensity at higher concentration, which I think it is not really a quenching effect at a high concentration, more than the higher concentration is either causing higher cytotoxicity in these high doses. Plus, so the higher cytotoxicity means you don't have enough cells to do the reaction, you will see less response. Plus, with higher concentration still over monolayers, you are going to produce, or there is a possible interference from the nanoparticle at these concentrations. Another assay that can be see different effect of nanoparticle interference here is LDH. LDH could be done as a total LDH, which we do a step of lysis, that we lyse all the content of the well, then we measure the LDH, and that's why it's called LDH content or LDH total. But other assay is the 2 milligrams, which measures the LDH released in the medium. So we don't apply any lysis, and we measure the LDH literally in the supernatant around the cell. These 2 assays have to be done while the nanoparticle in the medium. So there is no way I can get the nanoparticle out from the medium. So the total assay, as you can see here, increasing the concentration is associated with a low amount or low content of LDH. With some areas, with some bars or some concentration are causing significant decrease of LDH. This could denote the underlying cytotoxicity that denoted the response could be less, and the amount in these cells are less because we are losing the cells because of the cytotoxicity. But we expect to see a higher release at this high concentration. When we look into the release, we see increasing concentration is associated with increasing the release, but never the release is amounting to the negative control, which is this red bar, never, which denoted there is a possible interference or absorption effect of this LDH around the nanoparticle, with the nanoparticle still in the medium. So it was an easy way to spot the interference that can happen with the nanoparticle in the release assay. Now, because you will see some of the literature are presenting the nanoparticle LDH release assay as not causing any issue, while this is literally could be a denoting effect of nanoparticle absorption to this cellular protein, giving a false negative response. At the end of this, we can expect some question when you need to drop any question. Thank you very much.